Hi everyone, welcome to 5.3, where we're going to be talking about software engineering principles. I've just sent a poll for the persistence lecture, by the way, in the chat, so if you could fill that out, that would be great too. Would love to get your thoughts. So this little lecture is touching on a topic that I don't think is covered enough at university, and honestly it's really hard to teach it to like people largely in first or start a second year, because I think you learn the most about software design when you've written a lot of bad software. You know, like if you try and teach someone, it's like one of the reasons again that I don't do lectures on like teamwork, like how are we going to function as teams, is because I don't think it makes a lot of sense until everyone runs into teamwork problems, you know, because I think it's very hard to teach someone who hasn't had good or bad experiences, like people who in general haven't had real good or bad experiences, about how to have good experiences. And it's kind of similar with software design. It's really hard to like emphasize to people like why this is better, why this is cleaner, if you haven't written a lot of good code and bad code. But we do a little bit of it anyway. This falls under the SDLC design banner, which is basically saying like, you know, we're interested in designing good software. Like we can code software well, but we want to have like a good structure in place to code, because you can actually code really well. You can effectively, cleanly code poorly designed software, right? And we'll talk about what poorly designed software is. So the first thing is, sometimes there are these things what we call design smells. We call them design smells because there are things that we kind of notice in code, and you know, we use the term smell because it kind of stinks. You know, it's kind of like if you smell something, like if you're in the kitchen and you smell a bad smell, you're like, oh, something's wrong, you know. And it's a similar thing with software design. Now, I won't lie to you, a lot of these things are pretty similar. Most concepts of good design come down to fairly straightforward principle, which is that well-designed software should be easy to change, easy to separate, easy to understand, easy to reuse, right? So you got some things here like, you know, immobility says previous work's hard to reuse. Fragility, which is a tendency for software to break when a single change is made. We got the simplicity stuff, which is like opacity and needless complexity. Like we want things to be clear and simple. We know repetition is bad because redundancy is bad. Coupling is a form of fragility. Like there's a little bit of overlap here. Like these aren't like the 8 golden rules of design smells. It's just like, here are some things to get your brain thinking, because there's more than this as well. But generally, code repetition bad, complexity bad, writing code that makes any changes to it break stuff is bad, you know, and kind of more. So, you know, and again, just some other terms here. We want to try and make our code understandable, which is, you know, simple. Maintainable, which again means you can change it easily without it breaking. Reusable, a good example of reusability is breaking code up into functions so that you can reuse those functions. And extensible, which I think kind of has a bit of an overlap with maintainable, which is kind of just like you want to be able to add more things. If anyone's worked on large software projects before that aren't well designed, you know what it's like, where like the bigger it gets, it's kind of like one of those, it's like a house of cards, right? Like the bigger it gets, the slower it is for you to do everything, because you're always scared about breaking something, and that's what we don't want. Most of the time we can solve our software design problems by applying some fairly basic abstraction principles. You know, things being testable can often be solved with abstraction. Things being maintainable can often be solved with abstraction. So abstraction is a huge part of like how we solve some of these problems. And we're going to go through just like a few key things here, like a few different concepts. In this course, we keep the concepts really broad and high level because, again, you're quite early in your journey of software in the scheme of things. But the first one's called DRY, which is don't repeat yourself. And this is essentially just the principle that says every piece of knowledge and information should have a single, unambiguous source of truth. You know, we use like in work, we use the word source of truth, or like, one source of truth or whatever very often to kind of say, you never want to do something like have a secret twice in your code. Or if we go back to VLab here, where I had a look at this auth simple, you know, you don't want to put a save function at the bottom of every single route. You don't want to have like a token being generated in login and register when you can abstract that into a separate function. Like everything you do in your code should be done once, like kind of full stop, because you want it to have a common source of truth. And that's what helps make your code maintainable, because if things change, they only have to change in one spot. So dry is a pretty big principle. So if we look at a really simple piece of code like this one here, oops. I really think what I must have done last term is saved, or like saved over all of my week 5 code. But yeah, let's have a look at this one. Just looking at the persistence poll. How did that go? That wasn't too bad. Okay, so look at this code. Pretty simple. Well, no, it's not simple at all. It's like, okay, we read in from sysargv. If it's not equal to 2, we crash. We get the number. We get a num from sysargv. So it's like the first command line argument you enter. If the number's 2, we loop through the numbers 10 to 20. We get the squares of all those numbers and we print out a result. If the num's 3, we go from 10 to 20. We print out all the cubes of those numbers, and we print out the result. And then if the number's not 2 or 3, we exit. It seems like a weird program, but also it's like this is the kind of program that a lot of students would write. So if I go Python 3 dry.py, if I don't give it command line arguments, it exits. Remember, actually, I can show you this. Remember how I said yesterday that programs like succeed or fail? Watch what happens when I write that. It says 130. Why does it say 130? Oh, 1. I think it's probably because I started typing more. Yeah, so you can see our program's actually returning 1. So this is actually how like we in Python would tell the Unix system or the terminal or the shell or whatever that something's gone wrong. So because the sys.argv is not 2, it crashes. And how do we make it 2? Well, if we add 2 arguments here, it's going to crash 2. But if we add 1 argument, then it works. If that argument we add is not 2 or 3, then it won't do anything. So slow. If it's not 2 and it's not 3, it won't do anything. If I add 4 or I add 1, it crashes. Right? So that's the behavior of the program. Now, the rest makes sense. If it's 2 or 3, we loop 10 times, we print out the squares or the cubes. 2 means squares, 3 means cubes. How do we how do we avoid repeating ourselves in this software here? Like, tell me, where are places where we're repeating ourselves? I know there's the YouTube lag and all that. Use variables for multiple. For the multiple. What do you mean by the multiple? So I like Joshua's answer, because Joshua says, I mean, you've all said it in a different way, but Joshua's very clear. He says 2 and 3 are the only thing changing in that. Exactly. And all of the rest of you are all saying the correct things as well, which is like the only difference between numbers 2 and numbers 3 is this 3 here and this 2 here. Right? So if I wanted to, I could say, all right, well, if num is equal to 2 or num is equal to 3, I'm going to do the exact same thing, but instead of using 2 here, I'll just use num. Okay? Done. Easy. Right? That's a simple way to start. How do we avoid repeating ourselves too? Who was it that said TTTKKK said we say sys.exit twice? That's true. So up here I might make a function that's called like crash or something, and that'll just be sys.exit1. And in these 2 cases here, I'll just crash like that. So now we've avoided repeating ourselves. And I think that's kind of the main stuff. I don't think there's much else you would do. Griffin has said, you know, rather than do this, maybe we could do something that's like a little bit cleaner, which is like if num is in 2 or 3. It's probably a good idea. It's a little bit easier to read and it's a bit more expandable. Like, what did we say back in these slides? We said we want software to be extensible, right? We want to be able to extend it. I think that's what that means. Anyway, regardless, that's what we want to do. So here it's easier because maintainability is better, because if you want to do 3 or 4 or 5, you can just add it. You don't have to like add another or dir equals dir, right? Charlie says, why is it better to replace system.exit with crash? I love that you asked that question, Charlie. And the short answer is it's barely better and arguably not better, which kind of ties into this whole concept about software design generally, which is about, there's a fine line between optimizing and improving your code and then over-engineering it. So like, here's an example of what I definitely consider to be over-engineering. Someone who says, I'm using sysargv twice here, so I'll create another variable called argv and make it be sysargv. Now the reason this is bad is because you've essentially added a useless abstraction, right? If you as a Python programmer see sys.argv, you know what that means. If you see argv, or like if someone even worse labeled this like CLI args or something, like command line interface arguments, you now have to re-establish like the semantics aren't clear, right? Like CLI args, you don't know what that is. If I showed you sys.argv, you're like, I know what that is. If I showed you CLI args, even if it's abstracted, it doesn't actually make programs that much easier to read because you're using like a well-established norm that doesn't require abstraction. So that one is not good. That one's definitely bad. For something like crash, I wouldn't call it bad genuinely, because like it's describing a behavior, and this behavior itself might be need to do more associated with it. I'd more call this one I'm pretty indifferent about it. Because, particularly if you're breaking things up into functions, particularly if you're doing something quite important, like exiting the program with an exit code of 1, it can be often very useful for these like higher importance activities to be abstracted away. Because failing to get these right could definitely be... But as I said, I'm indifferent. I think it's... Charlie said the right thing, which is like, there's that meme that's like, we were so busy... Yeah, we go. It's like, one of my favorite memes from... I don't even know. Is that Jurassic Park or Independence Day or something? Jeff Goldblum in the flesh. Yeah, this is a great... You should all print this out and stick it up on your wall. I guarantee it will save you at some point or another in your professional lives. Jurassic Park. Great. Yeah, so, this crash one, like, it's good to debate it. Like, these are the fun things to debate with people. Like, what's good design? What is improving our code versus, like, over-engineering it and making everything super complicated? Because some people out there might be like, oh, well, you can't really improve this much, but anyway, you get my point. Cool. Okay, so that's a very straightforward example of don't repeat yourself. We have another example here for dry, which is just our JWT stuff, right? So, dry 2. Is this it? It's loading. I kept rolling around on my chair before and I heard the sound of crunching. I had like Panadol, and like if you like roll over or step on Panadol, it makes this like just like that sound. And for the whole lecture last time, I was like every time I moved I heard it and I was like, I don't want to run over it. And then when I went to the toilet in the break, I like stood up and I was just sitting on it. So the whole time I was hearing it because I was just sitting on it. Thanks for listening. So now we have our JWT encoding decoding here, right? And this is another really interesting case of abstracting things out. So, this one's already finished here, but notice that like a mistake a programmer might make, for instance, is putting the secret here. Like they just put the secret in this place. But as again, like don't repeat yourself, the basic principles, like you've even learned this in 1511 is like, hash defines and stuff like that. We want to abstract these things out. So for most of you, it should make immediate sense why this is valuable, and you probably would all do this anyway. It does lead to that interesting question again, which is, do we need to abstract away the HS256? Right? Like, should we put that into a variable that's like JWT algorithm? Now, again, these are those interesting questions to ask yourself. Software design is a conversation, right? It's something to always talk to people about. And, you know, in this case, like, my instinct tells me no. And the main reason is, again, because, like, when someone reads this, they're going to have to think, Jesus, what's the JWT algorithm? I'm going to go and have to figure that out. But more importantly, and I think this one is quite critical, if you avoid repetition in all the logical places, repetitions like these don't hurt you as much. Because if you, like, take your project, for example, if you effectively correctly abstract JWT encoding and decoding, then there should only be one place in your entire project where you encoded JWT, and there should only be one place where you decode it. So therefore, the repetition of HS256 only happens once, you know? So, like, the impact of it is quite low. But if you weren't actually abstracting the JWT in code, like if you had this many times throughout your code, then you might be motivated to abstract this because you're like, I'm repeating it dozens of times now. So, you know, again, you just have to think about, like, where is a good balance here? Because if you abstract away this function, then you probably don't need to go crazy and, like, over-engineer it by abstracting away these variables, like HS256. Cool. We have just a few more principles. It's really not a ton here. The next one is called KISS, which is keep it simple, stupid. I mean, this is a term you might have heard used regularly in life outside of software. But this basically just says that software works the best when things are kept simple. Complexities and errors are correlated is the general theory, and I think that's absolutely true. So you always want to approach software in the simplest way. As in, if someone says to you, look at my complex solution to this problem, you should think, you suck, you know? Like, you should be like, that is not something to be excited about. You know, like, simplicity is this thing that you should chase, and we should all chase as much as we can, because when you write complex code, no matter how smart you think you are, it's going to have a higher tendency to have bugs and other issues associated with it, right? So you always want to be thriving, and you want to push the people around you to be thriving to write simple software. And this is like one of the problems when, again, you come across like young developers, particularly talented young developers, because they kind of take pride sometimes, and you see this in industry too, take pride in like doing tricky things. You know, it's kind of like a rite of passage. It's kind of like a badge of honor that, like, look at this like really complicated software I wrote because a novice couldn't write this. But you want novices writing code. Like, you want experts writing simple code, you know, and it takes a lot of brains to write simple code. There's a great quote I love. It's like one of my favorites, which is every line of code you don't write is bug free, which is an extremely true thing, because like when we say like, oh, you know, write less complex code, often writing less complex code means writing less code. And the less code you write, like if you write 20 lines of code, if you write 40 lines of code and then your team member writes 20 lines of code, your team member has 20 lines of code that are bug free, which are the 20 they didn't write. You know, because code you don't write, like, can't have errors in it. So we like to keep things quite simple. Now, how does this translate? We have a few examples here. We'll probably only go through the first two. And in some ways, this is actually us talking a little bit about Python libraries as well. So example one, write a Python function to generate a random string with up to 50 characters that consist of lowercase and uppercase characters. Okay, so I'll just show you this one. Really? Yeah, okay. So what was the question? Was I'll just copy this in. Write a Python function. Generate random string. Okay, well, let's get all my characters, right? I'll do this the fun way. I'll say all my chars equals, like, what? It's just going to be a string of A, B, C, D, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z, and then we'll do the same thing. I don't know. That's probably all of them, right? So we got all of our characters now. And it says to generate a random string with up to 50 characters that consist of whatever. So now I might make a function called like rand string, which might be like for I in range of 0 to 50. So we'll get 50 characters, and then we will create our return string, which might be blank, and then every time we do this, we might append one letter to our return string. But what are we going to append to it? Well, remember, a string in Python is also a list, so I could say like chars0 here, for instance, which will just create a output string of 50 characters. So if I run this one, kiss.py, let me run this properly, and I go print rand string, right? I get a. Oh, what have I done? Sorry, it's meant to be plus equals. I should say plus equals because we're like appending to the string. So I got like a. Now there's also a Python library called random. Heaven forbid you tried to write your own random number generator in Python. But there's a random module in Python, and there's lots of functions, but like one of them's randint, so we can get a random integer if we want. So we could import random, and then we could use a randint, which will give us a random number between 3 and 9. So here, instead of the index being 0 as in the first character A, we could actually say, let's do a randint between 0 and chars and length of chars, right? So now we can randomly generate this. No. What's the problem? Does it need to be like length minus 1 or something? Okay. Yeah, okay, there's a random thing. Kind of looks like a hash, doesn't it? Okay, but let's try and be smarter. Now, you can obviously Google this solution, so I might just do that and we can work backwards. Python random string. Here you go. Python random string generation with uppercase letters and digits. And then we look at this and we got some crazy person here who's just like, what? They're like, here, you can just do this. And we're like, really? So, we'll just like paste this here. We'll just say return this random piece of code off the internet. And you can see they're importing two libraries here, which is random and string. So I have to import string as well. Then we run this and we're like, n is not defined. Oh, n is like meant to be 50 here, sure. And we're like, God damn it, look at that. It just generated a random string. Aha, but it's not good as ours because this one is uppercase and numbers. But then you look at this and you think, oh my God, look at that. They're actually like, they're like passing this in. So what are we doing here? Well, let's take a step back. Let's first say numbers equals this, and then join numbers, and then we'll go print numbers. So calling random.choices. What random.choices does is it basically takes in a list, and then it will randomly select items from that list k times, which in this case is 50. And in fact, like we could replace this list here with like, A, B, C or something if we wanted to. So now it's randomly picking 50 ABCs from that list. Pretty straightforward, right? But what's really cool is in the string library constants Python, there's a bunch of properties. Remember when we talked about objects, we said there are like object functions and object properties. There are a bunch of properties that exist like ASCII lowercase and ASCII uppercase and ASCII letters and digits and hex digits and oct digits and punctuation. So we can actually just use these. And remember how we said we wanted it to be uppercase and lowercase letters? Well, we can just use ASCII letters here. So giving random choices, we could just say, I just want to get all of the ASCII letters in Python. I want to make 50 choices out of that. And then they're my numbers. And then this join here, all this join does is basically tries to join every single number in that list together with a blank string between it. So now when I run this, it's like, should work fine. Blab's slow. So yeah, now it works fine. And you can just keep code so damn simple. Like this is all this needs to be. And you can think about keeping it simple in terms, don't don't write 10 lines when 3 would work, and that's definitely true. But the reason I want to show you this example is because realistically, when you're working with Python, a huge thing that you're going to do to keep things simple is to use libraries, particularly these standard libraries like random, string, date, time, and stuff that will simplify your life. Okay. Next. Write a function that prints what day of the week it is today. Well, I mean, this one I wouldn't even know how to do without the libraries, but, you know, let's try it out. Let's see if we can do that. So, good old VLab, take your time. Oop. Alright, damn it. Alright. Well, it's here. What do we know in Python? We know that there's a datetime library. And then if we print out datetime now in Python, we get, it prints out like the moment in time right now expressed as some kind of string. But Python has a very powerful, like a Python datetime has a really powerful object method on it called string format time. And there's usually some easy resources you can find online. This one's a great one, stringformattime.org, where it actually shows you how that you can like take a Python datetime at any moment in time, such as right now, and you can print out any kind of crazy string you want. So like for instance here, you know, if I want to get like, okay, I want to get today's abbreviated name, so I can do like, you know, %A, and then I want to get the month's abbreviated name, and then I want to get the hour, you know, 24-hour time with a 0 padded, and I want to get the time zone name, which let's not do that one. Or I want to get like the day of the year. Like, I can just do this. And in Python, it will take a datetime object and it will output it to a string for me. Tuesday, March 11. What's 11? Oh, it's 11 a.m., right? At 075. That's the 75th day of the year. If you just print a Python datetime object by itself, it kind of automatically string formats time things based on like a predetermined structure. Like this one here, you could make this yourself with string format time. And in fact, let's try it. It's year, month, day. So we'd start with year with century as a decimal number. Great. So we'll do year dash and then the month, which is usually %m. Month as a 0 padded, and then we'll do day as a 0 padded, so we do %m, %d, space, and then we do, looks like hour, minutes, seconds, and some kind of decimal. So hour is capital H. What's minutes? Minutes is capital M, and then seconds is capital S. Oh, and it says dash seconds is a decimal number. Well, let's just start with, what was it? Hour, minute, seconds. Yep, 1133, that works fine, and now we're just missing the decimal part of it, which I'm not really sure. Microseconds is a decimal, %f. We could try that one. .f. So this is probably Python's like datetime, like default datetime, I would guess. Like, we could try printing them both out. Like, let's just print out one without the format time. Oh, well, I mean, they're the same, obviously. They're just processing like milliseconds apart or whatever. Less than milliseconds. Okay, so it's another way of keeping things simple. You know, you just use like more and more libraries. Another one which I don't want to spend the time on because I think we've dragged on a lot of lectures this term, is how do you handle command line arguments? Like if you wrote a program that was meant to kind of like emulate Git and you had a file called commit.py, how do you take in command line arguments, right? Like you know that Git has like different commands and different arguments, and there's actually a great library called Python, I don't know what it's called. It's probably here. I probably already wrote it down in the slides. No, I didn't. But it's going to be like Python command line arguments. There's usually some library in Python that lets you argparse. Thank you. So argparse is a really cool library where you can actually just like specify different types of arguments that you want the command line to be able to take. And then like it will automatically produce things like if you do dash help, it tells you what kind of things you can put in and like so forth. Because you could imagine that to write your own thing where you kind of like manually parse argv properties and all their different combinations would be very complex. And again, that is the opposite of keeping it simple. So that could be a fun thing for you to play around with. Okay, the third topic, encapsulation, whereby encapsulation is maintaining abstraction by restricting direct access to internal representations of types. Now, you all kind of get this because in a lot of ways, your iteration 1 was just a big abstraction of implementations, right? Like you had your interface, and that was hiding the details so that, you know, you or another group or any other group, we could take all of your different implementations and we could all run them and we'd expect the same behavior because they've all been what we call encapsulated, right? Under some kind of definition or type definition or interface. Most of the time you hear encapsulation, and you'll run into this more when you do 2511 this year or next year, probably this year for many of you. We actually often will use like classes and objects as forms of encapsulation, whereby like what we'll do, and I'll just briefly touch on this because it's not critical to the course, is encapsulation. I don't know. Oops. You know, if you have a piece of code, oh my god, just copy. I know I'm on VLab, but like, still, what is wrong with that? Okay. So, you know, if you have a simple class like this, and classes we didn't really go into, but something like that you'll commonly do is, with classes is, you'll try not to access the actual like underlying variables directly. And again, you should all be able to empathize with this because of what you did with the project, whereby, you didn't access the data store directly. You know what I mean? Like you used like functions to access it. So similarly here, if you were doing stuff with classes, which again, you'll do more in 2511, you might do something like this where you actually have a getter for get X and for get Y. So that when you're using it externally, instead of trying to access the underlying data, you would actually use get X and get Y here. So this is kind of like rules of encapsulation 101. And again, I don't want to talk about this a lot because we don't do classes in this course, but this is just an example of where it could be applied. But a lot of what you did in iteration 1 was encapsulation just by the nature of that you're encapsulating an implementation underneath an interface. This is another class example, but I don't really want to do it because again, like I keep cutting out class content every single term because there's already enough in this course. So I'm probably just going to skip over this one. I'm going to make a note of that. Cut encapsulation Q example. But you know, so encapsulation, it's hard to talk about that a ton without doing classes, but also like again, I don't think it's that hard because you're all kind of familiar with it. Encapsulation and abstraction are kind of the same thing. Abstraction is just a more general term we use to describe it, but encapsulation specifically saying like this is a type of abstraction where I'm trying to hide the implementation details with some kind of type interface. So the last one is, which I think is super interesting. Last one for today is like what's called like top-down thinking. And I call it top-down thinking, but the actual name for this in like textbooks and stuff is like you aren't going to need it, which basically says that a programmer should not add functionality until it's needed. And it's a really good principle to live by because it's like a common source again of complexity in code or design problems are people trying to over-engineer things or write things that aren't needed yet. In a product design world, typically one way this manifests is that, you know, if you have a front end over here and you have a server, top-down thinking is let's build out the interface first. And then let's see what data the interface needs. And then let's write a route for it. And then let's implement the route to get the data. right? Because in this sense, like, we are trying to actually build something for people to use and then figure out what they need. That's like top-down thinking. You're approaching the problem top-down. Approaching the problem bottom-up is saying, you know what? We're going to build this application. Let's make a server with all these HTTP routes in it that they can use. And we'll just build it all up, and then we'll get to the front end. And the problem with that is when you go and build the actual like top part of your application, sometimes it's not a front end. Sometimes it's just the higher level functions in a program. You know, what happens is you miss stuff. There's stuff that you didn't have, and then also there's a whole bunch of stuff you implemented that you just don't need in the end because you approached it from the bottom. So it adds unnecessary bloat to your software. Yeah, so when building capabilities, we should work from high levels of abstraction down to lower levels of abstraction. Now, this doesn't necessarily always mean that you have to write a front end first. Like, that's not the point of this, because that's a very broad example. But a more literal example is if I said to you, I want you to write me a program that, given 2 latitudes and longitude coordinates from, say, the command line, finds out what time I would arrive at my destination if I left now. Now, this is a complex problem. And like the weather activity is also a complex problem. And the way I always try and approach these problems is you always start from the highest level. You like, if you start these problems being like, I'm going to go and figure out how to calculate latitude, longitude distances, it's probably not a terrible idea, but it's good practice to say to yourself, let's try and write code from the top down. So if I was writing this piece of code, say in another file here, and let's imagine that these things are passed in on command line, right? So I might say, you know, import sys, and then I'll say I want to get them from command line, because top down is thinking like you got to think about it from the user first, right? So what's the most basic function? It is that I would, if name is main, I'm going to get, I could write this a bunch of different ways. I could say, you know, if sys.argv, if the length of sys.argv is not equal to 5, which is like the name of the file plus 4 command line arguments, then I want a sys.exit. But if it is 5, then I can say I'll pull like lat1, long1, lat2, long2 from sys.argv from 1 to 5, right? This is a fancy way. This is just like, this is basically me taking sys.argv, all 5 elements, stripping off the first, and then unpacking it into these 4 variables. And like I'll show you this quickly. Like it's quite simple. So I'd say like Python 3 lat long 1 2 3 4, like that. Now what am I going to do with those? Well, I'm going to say, what's the question? It's given 2 latitudes. Find out what time I would arrive. Time between, right? So I'm gonna basically create a function here that I haven't written, and this is one of the big ways to approach things top down. You write functions that you have no idea how they work, and you just keep writing them, and you keep writing them, and eventually you'll have finished your software. So I'm going to write a function called, I'm going to print time between, and time between is going to take 2 tuples, the first lat long and the second lat long, like that. And that's all it's going to do. Great. So then I write this function up here, def time between, which will take in place 1, place 2. And what it's going to do is return 1. This is how, like, and now I describe this to, I used to describe this to students. It's like, I finished my program, it just doesn't work yet, is how I think about this. Because you've kind of actually done the whole life cycle, right? Like the reading in, the calling a function, the printing it out to the user. It's just that it doesn't work yet. So, you know, it just gives me 1. Because I've solved this problem at the highest level of abstraction. And then we need to ask ourselves another question, which is, you know, how do we actually get the value? So I want to find out what time I would arrive if I left my destination now. Well, actually, I've done something bad here. Sorry, I haven't quite finished this because, you know, I'd say like time taken equals this, because time between gives me the time it takes to move between 2 points. And then I might say print, you know, arrival time from now, where I give it time taken. And arrival time from now is going to be another function that just takes in like time taken. And this might be like something. So the point of arrival time for now is to pretty much take a date time in Python and add time to it, which God, I don't know how to do this. Like, let's assume that time between returns seconds. I'm not sure what the specific method is for date time, because I think it might be like return date time dot now plus date time dot time delta seconds equals time taken. I think that's it. I don't know. I don't do a lot of Python these days, but let's try that out. This should print out, I don't know, now, but 60 seconds or maybe an hour in the future. Huh. Okay, that worked. Didn't expect that. So, but previously though, we'd stubbed these functions, and again, we'd finished the program, we'd gotten the logical flow right, we just hadn't filled in some of these like implementation details. So we're trying to work down through layers of abstraction and get lower and lower. So now we do the time between. Okay, well, lat one long one equals place one, and lat long like that. How do we find the distance between these 2 points? Well, and how do we know how long it takes? Well, what do we know? We know that, what is it? Speed equals distance over time, right? Okay, so what is time? Time equals distance divided by speed. Okay, we know that, and we're trying to return time. So we know that we're going to return distance divided by speed. So now I'll say distance is 1 and speed is 1. Right? So again, I'm trying to break this problem down without getting too lost in it. And I haven't really solved many problems here, but I've actually written the software. So, okay, distance is 1, speed is 1. It says that, assume that I can travel at the country's local highway speeds. Let's just call this 100 kilometers an hour, right? So speed will be in kilometers an hour and distance will be in kilometers. Well, what's the difference? Distance. Okay, well, maybe here I will call another function called lat long kilometers apart or something. Now you could argue this might be like an unnecessary abstraction, and it possibly is, but I'm just trying to demonstrate the point, where you might add lat 1 long 1 lat 2 long 2 or something like this, right? So this abstraction I'm not too thrilled about, but it's not terrible, because you're separating the calculation of time from the calculation of distance. And then what this might do is this might return 1,000 kilometers. So if this returns 1,000 kilometers and my speed's that, then it says it's going to take me 10 seconds. The problem is that I'm returning this assuming it's seconds here, but what this is actually returning me is hours, so I need to multiply this by 3,600. So it actually is kind of interesting. Like if I say I need to travel 5,000 kilometers, it'll tell me what time I'll arrive, which is 2 days from now. Cool. And this lat long thing, I mean, I'm not going to do it now, but it's like lat long distance formula, which in this Earth's radius, I'm checking out for this one. You get my point though, right? Like you can find these values around, and there's formulas for it, and this is what you plug in. So that's how you approach a problem top down. Yeah. It's a great way to think about software, because it can help you build confidence as well, because you can just say I'm gonna deal with what I know, and then work my way down. And it's really great too, because it tends to mean you always have software that functions. It's like this old trope, which was like how to build an MVP. This diagram's classic. Which is like, when you're trying to build software, I mean, this applies for all software, which is just like, if you're trying to build software, your aim should always be to build it such that while you're building up, each kind of stage generally functions, even if it's not quite what you want, even if it doesn't do everything you want. Like, you don't want to spend half your time building half a car that does nothing, So, yeah, that's interesting to think about. So that's pretty much it on the software, basic software design stuff. Most of the rest of the slides are things I've just talked about in general. So